Hello guys, today we were going to solve a sample problem in Chapter 7 of Thermodynamics and Heat Transfer, the refrigeration cycles. The problem is, consider a 300 kilojoules per minute refrigeration system that operates on an ideal vapor compression refrigeration cycle with refrigerant 134A as the working fluid. The refrigerant enters the compressor as saturated vapor at 140 kilopascals and is compressed to 800 kilopascals. Show the cycle on a TS diagram with respect to saturation lines and determine the quality of the refrigerant at the end of the throttling process, the coefficient of performance, and the power input of the compressor. The given values are: rate of heat removal is 300 kilojoules per minute, the pressure at state 1 is equals to 140 kilopascals, and compressed pressure is equals to 800 kilopascals. The TS diagram of the refrigeration cycle is shown. We note that this is an ideal vapor compression refrigeration cycle. Thus, the compression is isentropic and the refrigerant enters the compressor at state 1 as a saturated vapor. At state 2, the refrigerant enters the condenser as superheated vapor and leaves as saturated liquid at state 3 as a result of heat rejection to the surrounding, while in state 4, the refrigerant enters the evaporator as a low-quality saturated mixture. From the refrigerant tables in Table A-12 in our property table, we have saturated vapor at 140 kilopascals, which have a property of enthalpy at saturated vapor at 140 kilopascals is equals to 239.16 kilojoules per kilogram, and an entropy at state 1 is equals to our entropy at saturated vapor at 140 kilopascals is equals to 0.94456 kilojoules per kilogram Kelvin. In pressure 2, we have 800 kilopascals, which is equals to 0.8 megapascals, and our entropy at state 1 and state 2 is equals. By using the property of 0.8 megapascals in table A-13, we can interpolate to determine the enthalpy at state 2. In interpolating, we use the formula enthalpy at top minus its bottom over the value of our enthalpy at top minus its mid value is equals to entropy at top value minus its bottom over the entropy at top minus the mid value. Then plug in the values. We have 275.39 kilojoules per kilogram as our enthalpy at state 2. In saturated liquid at pressure state 3, which is equals to 800 kilopascals or 0.8 megapascals, we use the enthalpy at saturated liquid as our enthalpy at state 3, which is equals to 95.47 kilojoules per kilogram, in which it is given in Table A-12 on our property table. Thus, our enthalpy at state 4 is approximately equal to our enthalpy at state 3. So, our enthalpy at state 4 is equals to 95.47 kilojoules per kilogram, as also known as our throttling process. In determining the quality of the refrigerant at the end of the throttling process, the quality X is equals to enthalpy at state 4 minus the enthalpy at saturated liquid over the enthalpy at evaporation state. This property is also given in Table A-12 So plug in the values. We have 95.47 kilojoules per kilogram minus 27.08 kilojoules per kilogram over 212.08 kilojoules per kilogram. Then cancel out the same units. We have 0.322 as our quality of the refrigerant. Next is we use to determine the coefficient of performance of the refrigerator. By using the formula COPR, or coefficient of performance of current refrigerators, is equals to heat removal on a unit mass basis over work net input on a unit mass basis. Since heat removal on a unit mass basis is equals to enthalpy at state 1 minus to its state 4, then our work net input on a unit mass basis is equals to enthalpy at state 2 minus its state 1. So the equation is coefficient of performance of the refrigerator equals to enthalpy at state 1 subtracted to its state 4 over enthalpy at state 2 subtracted to its state 1. So plug in the values. We have 239.16 kilojoules per kilogram minus 95.47 kilojoules per kilogram over 275.37 kilojoules per kilogram. Cancel out the unit. We have 3.97 as our COP of the refrigerator. Lastly, the power input to the compressor is determined from the rate of heat removal over the coefficient of performance of the refrigerator. Then plug in the values. We have 300 kilojoules per minute multiplied to 1 minute over 60 seconds over 3.97, then crush out the same units. So we have 1.26 kilojoule per second or 1.26 kilowatts as our power input to the compressor. So that's it. I hope you've learned something. Thank you for watching.